Week, we learned about 5 different atomic models throughout history. This week, we're going to focus on why did the models have to change? Why do we need new models in science? So let's start at the beginning. For many years, people did not even believe in atoms. They believed everything in the world was made from 4 elements: air, water, earth, and fire. With a lot of experimentation, Dalton's atomic model came along. He had evidence in the lab. Water, which was thought to be one of those 4 elements, could be chemically broken down. It wasn't a fundamental piece. Okay? It could be broken down into smaller atoms like hydrogen and oxygen. In fact, it broke down in a specific fixed ratio. It was always 2 hydrogens to 1 oxygen, a 2-to-1 ratio, H2O. There was never half of an atom, or a third of an atom, or 1 3/4 of an atom. This led to a new model, the solid sphere model. An atom was like a tiny solid ball that could not be broken up into smaller pieces. But more scientists came along and asked the question, could there be something smaller? J.J. Thomson was one of these scientists. He was studying electricity. One thing we already knew about electricity at that time was that like charges repel and opposites attract. You might have heard of that phrase, opposites attract. It comes from science. He was studying electricity and these cathode rays, they look like a beam of light. And when he put charged plates, they always were attracted to the positive. And according to this idea, opposites attract. If something is attracting to the positive plate, then this thing must be negative, because negative gets attracted to the positive. He also found out that these particles that were negative in this beam were very small, smaller than oxygen and hydrogen and other atoms. So he has evidence. There were particles much smaller than an atom, and they were always attracted to the positive. Because opposites attract, the particles must be negative, and he named them electrons. So now we have something new. And this led to a new model, Thomson's plum pudding model, where you have this charged sphere. We still have a sphere, but it's positively charged, kind of like the pudding. And in that sphere of positivity, you have negatively charged electrons scattered like raisins in the plum pudding, or like chocolate chips in a cookie. Overall, the atom is neutral, still has positive and negative charges. But we didn't know a lot about that positive stuff. So more scientists came along. There's your plum pudding model. Now, Thomson had a student, Rutherford. Rutherford was going to study that positive stuff. He was going to study the atom and did a gold foil experiment that looks like this. He would take positive particles, and shoot them at gold foil and see what happened. A lot of them went through, most of them went through, but a few were repelled backwards. Let's look at his evidence. Rutherford, over 99.999% of the alpha particles, the positive particles, went right through the gold foil like nothing was there. Right? This is the gold foil atom. It went right through the atom. Why? Because the atom is mostly empty space. It's not air, it's actually empty. Most of the atom, 99.999%, is just empty space. And that's why those particles were allowed to go through like nothing was there, because nothing is there. But not all of them went through. He had more results. He found that every once in a while, the positive alpha particles were deflected or repelled back. Why? Well, it was hitting something positive, right? Positive and positive repels. So the positive charge hit a dense nucleus of positive charge and was repelled. And so he gives this little piece of the atom a name, the nucleus, and he says it must be positive. So this new evidence leads to a new model, Rutherford's nuclear model. So now, instead of the plum pudding, now we have an atom with a nucleus that's positive and electrons just whizzing around everywhere in a lot of empty space. But more scientists came along and have more questions. Bohr thought, if the nucleus is positive in the center and electrons are negative and spinning around, Well, opposites should attract. How come they don't attract and stick? Well, he goes in the lab and he gets some evidence. It's known that every element on the periodic table gives off a unique atomic spectrum. These are atomic spectra. They look like a little barcode that you might see on something you buy. Right? But where do these lines come from? Every element is unique and different, but where do they come from? And it's found out electrons. He surmises that electrons are arranged in circles around the nucleus, not just anywhere, but in circles, and each circle has a different energy attached. He also discovers that electrons can jump from one energy level to the next, and when they jump back down to a lower energy level, energy is released in the form of color or light, and that's how these lines get created. The electrons can't attract to the nucleus. They're traveling too fast in these energy levels to be stuck. This leads to Bohr's new model, the solar system model. You still have the positive dense nucleus, but now electrons are in more organized energy levels. They can move from level to level, creating those lines of color, but they are connected to energy. However, more scientists came along and have more questions. Oh, let me go back. But if electrons are orbiting the nucleus, then we would be able to predict their behavior, right? Well, they discovered that electrons sometimes behave like a wave, other times behave like a particle, and this duality was strange because normally things don't behave as matter, they behave as matter or energy, but not both. Electrons are starting to be unpredictable. And then you get Heisenberg's uncertainty principle that states you can predict an electron's location or momentum, but not both. So this is kind of contradicting some of Bohr's ideas about predictability. So their work changes things. And you have a new modern model of the atom, which shows a dense positive nucleus filled with protons and neutrons, surrounded by mostly empty space, where electrons move unpredictably in an electron cloud. And this is the model we have today. They're working on new models and gathering new evidence. But this is the modern quantum model.